Okay. Now let's come to the second order. Okay, so now it is sorry, there's no find the sum, and this 1 over n factorial becomes 1/2. Now you have integral 0 to 1 ds1 and integral 0 to 1 ds2, and now this p should act on a s1 and a s2, right? So this is the and so let's only come to this term and let's temporarily ignore the higher order. So this is enough to just look at second order. Higher order is more or less the same. So now this is a path ordered operator, if you like. Path order operator act on matrices. A matrix act on a matrix product. AS1 multiply AS2. Okay. So now how to define this? So here I'm going to give you a definition for that. So P AS1 AS2. Okay. So if you know some quantum field theory, this is just analog of the time order product. So these are here. The point is that there are two matrices, two non-commutative. Non-commutative matrices. An analog of in time order product. It is an operator product. They are non-commutative operator. Well, here it is when. So it relates to comparing parameter S1 and S2. Yeah. So when S1 is less than S2, it orders A S1, A S2. So you always order S, smaller s in front of larger s. So you always order smaller s in front of the larger s. So then suppose you have S2 is smaller than S1, then you have to order AS2 in front of A S1. Okay. All right. So this is the definition for the path order. So of course, there are some convention involved. It depends on whether you order smaller s in front of larger s or order larger s in front of smaller s. So here I'm just using the same convention as Tima's book. So of course, different book may have different convention, but here we always use the same. Try to use the same convention as Tima's book. Same convention as Tima's book. Okay, so here it is definition of the path order operator. Now we can compute this second order integral by plugging in the operator, this path order operator. This is base 1/2 integral 0, 1, 0, 1, ds1, ds2. P S1, 2. It equals to, you can split this sum because you see you have to take into account two different cases when S1 is smaller than S2 or S2 is smaller than S1. So you have to split up the integral into two different regimes. So S1 smaller than S2, S1, S2, S1, S2, plus the other cases. S2 smaller than S1, S2, S1, S2, AS2, AS1. Okay. Now, these are, we basically split up this integral into two different regimes. And in diagram, you can see that this is a two-dimensional integral of S1 and S2. So you are integrating a square, right? But here you have two different regimes, are basically two triangles. So this is the regime. This is the regime for this is, I think, it's S1 greater than S2, and the other is the S2 greater than S1. This is S2. Okay, but now for the second term, you can do a change of variable. Okay, so the second term, you can perform a change of variable using just replace S2 interchange with S1. You just call S2 S1, you call S1 S2. So it's change of variable. In the integral, of course, change of variable won't change the value of the integral. Then once you have that, you find the second term is just the same as the first term. Yeah, you replace all the S2 to S1. Yeah, you find these two terms just the same. Yeah, so these are these S1 is more than S2. S1, S2. Okay, now I can write it more explicitly because this is integrating a triangle. It is integral ds1 from 0 to 1 and integral ds2 from s1 to 1 because s2 is always larger than s1 and a s1 a s2. Okay, so now you see explicitly the second term in the holonomy when you expand the holonomy into polynomial of integrals. So this just gives this result. Okay, so now we can write more explicitly this holonomy. This holonomy equals to just one identity matrix plus a sum n equals 1 to infinity. Well, and all the higher order path ordering operator P works the same. You just permute the matrices so that it satisfies the ordering S. So this ordering, yeah, you should actually emphasize this ordering relates to the orientation of the edge. That's why orientation is very important. That's why we need orientation of all the edges. S1 into S1. And from S1 to 1 ds2 integral from Sn minus 1 to 1 dsn. And then a S1, a S2, a. Okay. So this is, here you sum over n from 1 to infinity. So this is the expression of holonomy, more elementary expression of holonomy. So I call this equation 1. So there's a well, here it is remarked that AS belongs to SU2, the algebra, and then holonomy belongs to SU2 group. Because this is just like an exponential map. Exponential map mapping from Lie algebra to Lie group. All right. So here I'm showing. So this is one way to compute holonomy, and there's another way to compute holonomy. Sometimes it is more useful than this formula 1. So I'm going to mention that in some calculations, this second formula, which I'm going to talk about, is more useful. To compute HE. So the idea of second way to compute HE is that once we have an edge E, oriented edge, and the parameter runs from 0 to 1, so you can cut this edge into infinitesimal pieces. So because we know this holonomy relates to a path order integral, and integral can be approximated by using Riemann sum. So it is integrating along a curve. So then it can be approximated by if we cut this curve into infinitesimal pieces, and it can be approximated by summing all those pieces and integrate only small pieces. So this is the first piece I will call S delta S1, and then delta S2, and so on, and then delta Si. And the last one is I will say delta Sn. Delta Sn. Okay, and then the holonomy. So in each infinitesimal steps, in each infinitesimal piece, you can approximately ignore the problem of non-commutativity of the matrix, because each piece you can linearize the holonomy, because holonomy is exponential. Well, and then because the path is very small, then the exponent, you see, the exponent, when this curve is infinitesimally small, then the exponent is very small. So this is exponential. You can linearize this exponential, and then once you linearize the exponential, and you don't need to take into account this path order already, at least approximately. So which means this H of E can be written as composition of all those small pieces, because you have an integral and it's at the exponent. And the idea is following: you have an integral on the exponent, and then you cut into small pieces, and then you write this integral as a sum, as a Riemann sum, as a sum, and each term in the sum is infinitesimal. And then it's the exponential of the sum. It means it's a product of the exponentials. Yeah? And on the exponential, you have, and each term is infinitesimal small in the Riemann sum. Then the exponent of each exponential is very small, and then you can linearize each exponential. Yeah? That's the logic. Okay, but you have to take into account the order of those delta S. So you have to follow the order, because although each exponent is linearized, but each exponent each contribution is a matrix. They are non-commutative. So I can write the holonomy as the following: S. So this is the, you can view, this is the holonomy along the delta S1, along the delta S1. Yeah, and because delta S1 is very small, so this exponential can be linearized. And then follow than that, you have to multiply delta S2 ds as, and so on. And plus delta Sn. Yeah, and this product, you have terms in the square bracket, but the product of all those square brackets has to be ordered, because each square bracket is a matrix. They are not necessarily commutative. So you have to order this product, and the ordering is respect to the ordering of the edge. Yeah? You have to, so the ordering of the edge tells you that delta S2 is after delta S1, and delta S3 is after delta S2. So then the integral of delta S2 is multiplied after the integral of delta S1. And in the end, you have to take the limit. Take the limit, n goes to infinity. You have infinite number of small pieces, where delta Si goes to 0. And you shrink each piece to 0. Okay, so here you can see well, you can also relate to the ordinary exponential, because suppose this is analog of exponential of x equals to limit n goes to infinity 1 plus 1 x divided by n to the power n. Right. This is analog of that. And this equation I will call equation 2. So second one, it is sometimes more intuitive. And so now this is your homework to check that the equation 2 equivalent to equation 1. So what you need to do is just expand this product and then take the limit. Homework to check equation 1 equals to is equivalent to equation 2. Let me see. I think probably here is a good time to stop. Yeah. So is there any question? So if you have questions, so you should ask. Okay. If there's no question, then I think we just stop here. So we continue next time.